Okay, welcome to the second video. We saw that in the previous video I introduced you to the that we are going to look at three different synthesis or design methodologies. The first one is basically a crank rocker design. The second is what we call as a path generation method, and the last one I think rigid body guidance or what is called as motion generation in the literature. Now, if you read a textbook like Robert Norton, he will get into detail about something called type synthesis, number synthesis. I'm not going to make this a very formal thing. I just want you to get introduced to the ideas that one could design these things without, and I'm going to keep myself to 4-bar mechanisms because that is what the focus is going to be in my lectures. So we are not going to do type synthesis, which essentially means finding what is the right mechanism. Is it a 4-bar? Maybe there's a 6-bar which can do a better job. It could be a cam type mechanism, it could be a gear type mechanism. So it's finding the optimal mechanism which will basically work with the uh, for the given design purpose. As I mentioned, we are going to limit ourselves to 4-bar mechanisms. We are going to understand how to accomplish this design using only 4-bar, and even more restrictive a 4R. If you want to use slider based designs, it is available in Norton's book. You can go read that up. So let's start with this crank rocker mechanism. And one of the things that you have been told, which we'll prove here, the first question that you ask is rocker basically goes between two extremes. I don't think anybody has any issue with that. That when we say it is rocking, it goes to one side and then it comes back to the other side. It goes to one side and then it comes back to the other side. Now, in either of these two extremes, what is the configuration that the crank and the coupler have? So this is the key question, right? And we need to prove that why is it that they take up such a configuration. So I'm going to first do this from an animation kind of point of view so that it becomes obvious to you what I'm trying to drive at, and of course I'll prove that using the concept of instantaneous centers. All right, let's go look at an animation. This is something that an animation that I made using a package called GeoGebra Classic. This is an open source package. This is available. You can even run it through the internet. You don't need to install it on your computer. You can directly run it off the internet. But I typically have it installed on my machine, and then I do all the work using this software. All right. So I will put up a video. I thought. It's not necessarily tied to the class lectures, but as a learning, I will put a tutorial on how to generate such a animation, crank rocker animation. I'll go through these steps, put up a video, which is how to use GeoGebra to basically generate such an animation. Okay, let's now look at the animation of the crank rocker. We'll open the media player. Yeah, it was open here, and you can watch as it reaches about 257, right about there. So I got it quite nicely this time. So you can see that this, I am claiming that of course the blue line is at the extreme position, which will become obvious as the crank rotates further. So this is one extreme position, and you notice that the crank as well as the coupler are along a straight line, right? So let me run the video further. You saw in the course of this animation up to this point that the blue rocker was moving from right to left. So now it will start to move back towards the right. You can see it is starting to move back again. Unfortunately, I'll stop here. So you can see it's still not reached an extreme position. That will happen right about there. Unfortunately, my timing of recording this thing is such that I stop it at when it reaches that extreme position. Okay. So the key takeaway, if you look at the key takeaway from the animation is that the rocker extreme positions correspond to or happens when the links 2 and 3, which are the crank and the coupler, are collinear. So this is a statement that I make, and what we are going to show why that is the case, and to prove this, we are going to look at the concept of instantaneous centers of velocity, which you learned just a week or 10 days back. We are going to use that. So this is another example that you will come across. Now let's look at the instantaneous centers for one of the extreme positions. So it is out here. I've drawn it. This happens at around 19 degrees. This is, it may not be, this 19 is a rounded off number that I read out from GeoGebra. So this in this configuration, you can see that effectively I have the black dots represent the four revolute joints, black circles, dark circles. So E is a joint between link 1 and 2, so that also corresponds to instantaneous center I12. I, which is the joint between 2 and 3, corresponds to instantaneous center I23. K is the joint between links 3, which is the magenta 1, and the 4, which is dark red. So that is I34, and H is basically the instantaneous center I14, which is a joint between link 1 and 4. Now, these by inspection are very easy to detect, and in order there are, if you know, in a 4 bar with 4 revolute pairs, you have seen earlier that there are 6 instantaneous centers for these for the 4 bar, and 4 are already marked by inspection, and the other 2 are I13 and I24. For us, the interest is I24 because I am trying to look at the relation between the input crank and the rocker output, right? So I am more interested in I24. Now, by Kennedy's theorem, I24 is going to be on a line. If you go back, let me draw the Kennedy's theorem circle. So the usual thing that we draw here, I have one note for the other position that I have already drawn, but we'll come back to that. But let me draw the Kennedy's, the various bodies. And what I will do is I will use blue colors to basically draw the instantaneous centers which are available by inspection. 1 to 4 we saw, 1 to 2 we saw, 2 to 3, and 3 to 4. Now the other instantaneous centers I am going to mark say with a green line. So you can see that if I want 2, 4, which is the green connection between this. So it is, if I look at that, if I look at this triangle, so it is on a line joining 1, 4 and 1, 2. And it is also on a line joining 2, 3 and 3, 4. So you can see that to locate 2, 4, I need to look at the instantaneous centers joining 2, 3, 3, 4 line and 1, 2, 1, 4 line. The intersection of these will basically give me the so if I do that, so I take 2, 3, 3, 4 and extend that line, and it intersects the 1, 2, 1, 4 line at I24, which is marked in red here. And what you have to look from this figure is that it is coincident with, for this configuration, it is coincident with I12. So I12 and I24 are at the same location. Now if I look at the velocity of I24, which is a point which is common to both link 2 and 4. It's a relative instantaneous center, remember. And if I treat it as a point on body 2, the velocity of this, remember every point on body 2 is rotating about I12. So if I want to find the velocity, the magnitude is going to be omega 2 times I12, I24, and is going to be perpendicular to that line I12, I24. Now in this particular case, I12, I24 happens to be 0, which means that the velocity of I24 at this instant is basically 0. Now if I treat this on the other hand as a point on body 4, I24 as a point on body 4, remember every point on body 4 is rotating about I14. So therefore, the velocity of this is omega 4 times I14, I24. And even though I14, I24 is non-zero, since the velocity is 0, this would imply essentially that omega 4 is 0. Now, if you go back to your simple calculus, omega 4 in terms of the angle is d theta 4 by dt. So if I say d theta 4 by dt is 0, I am at an extremum. So theta 4 extremum, which could be a minimum or a maximum, right? So I hope you are convinced that omega 4 is 0 at this configuration, which is why the rocker is at one extreme. The theta 4 has reached an extreme value, which is either a minimum or a maximum. All right. This collinear position is shown for theta 2 equal to 19 degrees. And one can convince that that it need we have a 0 there by looking at what happens at 12 degrees and 30 degrees. So I have plotted the configurations at theta 2 equal to 12 degrees. And you can see that in this particular configuration, I24 lies in between I12 and I14. So what this implies is that the angular velocity of 4 will be opposite to that of 2. So if 2 is rotating anti-clockwise, you can see that this is basically rotating clockwise over here. When I go to 30 degrees, I12 and I14 happen to be on the same side of I24, and therefore in this particular case, the angular velocity directions will be the same. So you can see this is anti-clockwise, and therefore I24, the link 4 becomes anti-clockwise. So at 12 degrees it was clockwise, and then at 19 we know it went to a 0, and then it changed direction and it became anti-clockwise. So you can clearly see that that is one more indication, a quick calculation that tells us that indeed we have a extreme position in between where the direction of rocking changed. All right, let's look at the other extreme position. So this is the other extreme position. Again, you can see I've sketched that in my, I have again drawn that here in my OneNote. So you can see I24 comes and lies right at the where I12 is, and that is what I have shown here. Little more nicely drawn picture compared to what I scribbled on that OneNote there. Okay, so in this extreme position also I12, I24 happens to be coincident, which would basically imply that omega 4 will be 0 at this particular position also. So therefore, this is the other extreme position. So we have two extreme positions, and in these two extreme positions, we can see that the coupler and the crank are collinear. So this is the key takeaway. At the rocker extreme positions, the coupler and the crank are in a straight line. So this is what is going to be the basis for our design. You see the simple geometry that we are going to use to come up with some wonderful designs. The other parameter that is taken into account in the design, which we have not talked about so far, is that it goes from one extreme to the other. So let's say in the animation that you saw going from let's say right to left is considered to be the forward stroke. So going left to right would be the backward stroke. Why do I say that? So let's go back. Let's look at that animation again. I'm having a counterclockwise or anti-clockwise rotation of the crank. So at the smaller angle, it is at the rightmost position, and then it moves to the left, reaches an extreme at around 257 degrees, and then starts to go back to the right. So this is forward ending, and now it is going back, which is the backward stroke. So so that is the kind of convention that I'm going to use to define forward versus backward, right? So let's go back here. So the time ratio is an important aspect of it. Now how do I use this? So if the time ratio is greater than 1, basically we will see that's called as a quick return situation. So let's look at these two extreme positions drawn together, right? So the angle between the two green lines, so this angle which you see, so this angle between the two green lines, that is between B1 prime O2 A prime or B1 O2 B1, this angle is alpha. Now the forward stroke basically happens from here to here, which is 180 plus alpha, and the return stroke is from here to here, which is 180 minus alpha. So this angle between the two collinear positions of the crank and coupler forms a design parameter alpha. So you can see that the time ratio is 180 plus alpha by 180 minus alpha. If alpha is positive, then I have a time ratio which is greater than 1. Obviously, if alpha is 0, I get a time ratio of 1, which means the forward and the backward are done in the same amount of crank angle rotation. And of course, you can have a negative alpha. Somebody will ask, okay, can alpha be negative? So yes, the forward stroke can be slower than the backward, the backward stroke can be slower than the forward stroke, in which case I get a time ratio which is less than 1. So you go back to your wiper problem. Think about this. Is the wiper a 1:1 ratio, or is it a time ratio which is greater than 1? Is it less than 1? Think about it. If not, go watch a wiper. If you have a car at home, just turn it on and then ask yourself whether it is a 1:1 or whether it is something different from one. So pay attention to that. We'll come back and I will post this question and then ask you during the live interactions. All right. So when TR is greater than one, we call it basically a quick return mechanism. If TR is equal to one, it is a 1:1 ratio. There is no quicker return. And the other case, of course, is a quick forward mechanism if TR is less than one. It moves faster in the forward stroke than it does in the backward stroke. Okay. So at the end of this, I would like to break. This is a nice point to close the video. What I would like to point out is that in this segment, I hope I have convinced you that the rocker extreme positions correspond to where the crank and the coupler are along a straight line. This is important for us to start the design. And there's something called a time ratio, which we will choose through this angle alpha. Setting that to be a positive value gives us a quick return mechanism. Setting it equal to 0 gives us a 1:1 mechanism. And if we set it negative, we get basically a fast forward motion. Okay. So from the next video, we will actually start the process of going through and designing the first approach to designing basically a crank rocker mechanism. All right.